This is the third and final part on the idea that the acceleration of an object is parallel to the net force acting on an object. We find that net force using vector addition. So far, we've learned the head-to-tail graphical method and the parallelogram graphical method for adding vectors. Now I'm going to show you how to do the numerical method for adding vectors. If you're going to measure a force, you need a unit to measure it in. The SI unit for force is called the Newton, abbreviated as a capital N, newtons. The Newton obviously is named in honor of Olivia Newton-John, American actress and singer, whose 1981 hit single, Physical, which became the #1 pop song of the 1980s, was inspired by her love of physics, her favorite subject in high school. So for increasing public awareness of physics and contributing to science education through pop music, we named the SI unit of force in her honor. So, an example of how to add vectors numerically. Here's a free-body diagram for some objects here with two forces acting on it at the moment. And I'm giving you the values of the components of these two forces. F1 has X component 4 newtons and Y component 8 newtons. On this scale, one grid space is 1 newton, so that's 4 newtons this way by 8 newtons that way. Force 2 here has X component 12 newtons, Y component 4 newtons, so 12 newtons this way, 4 newtons that way. We want to add these two vectors and get a numerical result for the net force. Let's start by doing the parallelogram method to see what the net force here is going to look like. I can tell that it's going to kind of point off in this direction because that's the way they're both pushing. So let's see, let's make a parallelogram out of this. Draw in a side here, parallel to F1. In fact, that should be the same force as, or the same exact shape as F1. And then the other side here, side parallel to F2. There we go. And the sum of those should be the vector that points from here to the opposite corner, the diagonal. This is our net force. Okay, and I'd like to look at the components of our net force right there. So let's make that the hypotenuse of a right triangle with that leg and that leg. So we call this leg here, that whole distance, that is the x component of the net force x component, and this here is the y component of the net force y component. And by comparison, we can see how to calculate those two components. Looking back here at F1, we could break that up into its x component, that's its y component, F1y, and this here is F1x. Now comparing this vector to this line here, we see that this distance is the same as that distance. This is also F1x right here, and this is also F1y right there, same lengths. Likewise for force 2, this is what we would call the x component of force 2. There's F2x, and then this right here is F2y. So visually, we see that the x component of the net force is exactly equal to F2x plus F1x. That gives us the net force x component. Likewise, in the y direction, F2y plus F1y gives us the y component of the net force. And so, summing the two up here, we can get the x component of our net force just by adding these two x components. 12 and 4 gives us 16 newtons. That's the x component of the net force. Summing those two, the 8 and 4, I'm out of room. We get 12 newtons for the y component of the net force. What we've done is found the sum of multiple forces here by adding up their components. The x component of the net force comes from summing the x components of all the forces you're adding up. The y component of the net force comes from summing up the y components of all the forces you're adding up. We call this adding forces component-wise. So with these two components, 16 newtons and 12 newtons, the components of our net force, here I've redrawn that net force, 16 newtons and 12 newtons. We can then combine those two components using Pythagorean theorem to find that our net force has magnitude 20 newtons. And again, using some trigonometry, figure out the angle right here that it's making is about 37 degrees. And report that the net force, the sum of F1 and F2, gives us 20 newtons at about 37 degrees above the x-axis right there. And why, of course, do we care about that net force? Because at every instant, an object accelerates parallel net force. The acceleration of this object will be in that direction also at this instant, at about 37 degrees above the x-axis. There we go. That's the numerical method for adding vectors. Here's a couple examples for you to try, a couple practice problems for you to try. Okay, in this first problem here, I've given you two forces to add. Find the net force, find the magnitude and the direction of that net force. Here again, we're using a scale where one grid space equals 1 Newton. Go ahead and do this one first, and then we'll talk about number 2. Pause the video, get yourself some graph paper, and using any means that you like from the last 3 videos we've watched, find the magnitude and direction of that net force. Ready? Here's the result. I've done the parallelogram method here to draw in the net force and use the grid to count up that its components are minus 1 Newton in the y direction and minus 4 newtons in the x direction. So with Pythagorean theorem, add those two components and find that the magnitude of our net force here is 4.1 newtons. Then do some trig to find this little angle right there and report that this net force is pointing at about 14 degrees below the negative x-axis. Okay, number 2. Here I've given you 3 forces acting on an object at the same time, and I would like you to find the direction of the acceleration of that object. This time I've given you the forces in terms of their components. Here is F1x and F1y, F2x, F2y, F3x, and F3y. The components there, and all of these are in newtons. So x component, comma, y component. Add those 3 forces and use the result to find the direction of the acceleration of that object. Pause the video, go ahead and do that. Ready? Here's the result. To add forces numerically, we add up the x components. The sum of these 3 here gives us minus 2 newtons in the x direction. The sum of these 3 here gives us about 4.7 newtons in the y direction. So those are the x and y components of the net force. I want to draw that net force, minus 2 in the x direction, plus 4.7 in the y direction. So our net force is pointing off in this direction here. Use a little bit of trig to find that this angle right here is about 23 degrees. Therefore, the object will accelerate parallel to that net force, so at about 23 degrees to the left of that positive y-axis right there.